No, it is not legally permissible to move an existing load to the generator in the scenario described. The primary reason stems from the limitations of the generator's capacity and the existing load it is already supporting. The electrical system in question consists of an 800 amp service operating at 208/120 volts, 3-phase power. A fuse disconnect protected by 225 amps fuses branches off from the main distribution panel and feeds a 225 amps automatic transfer switch, often abbreviated as ATS. A generator equipped with a 225 amp circuit breaker also connects to this ATS. The ATS then supplies a 225 amps power panel, which utilizes 3-pole fuse disconnects. The loads connected to this panel are primarily motors and air conditioning equipment, which operate continuously. Calculating the load based on 125% of the nameplate ratings of the connected equipment results in a total of approximately 220 amps. This suggests that the panel is nearly at full capacity. However, the actual load drawn by motors and air conditioning equipment often is less than their nameplate ratings. Furthermore, the calculation of 125% of the nameplate provides an additional safety margin. Consequently, the generator and the normal power source are only experiencing a load of approximately 110 amps. The desire to add an existing load to the generator raises concerns about exceeding the generator's capacity. The fundamental problem is that the generator is only rated for 225 amps. The existing load already draws slightly more than 110 amps. Adding any additional load would likely overload the generator. Overloading a generator creates a significant safety hazard. Generators are designed to operate within a specific range of current and voltage. Exceeding these limits can lead to overheating, potentially damaging the generator itself, the connected equipment, and the wiring. Furthermore, an overloaded generator may not be able to provide the necessary power to all connected loads, leading to voltage drops and equipment malfunction. From a code compliance perspective, the National Electrical Code, often abbreviated as NEC, mandates that generators be sized appropriately for the loads they serve. NEC Article 445 covers generators. It contains requirements for sizing, overcurrent protection, and installation. It would be essential to consult the specific sections of Article 445 to ensure code compliance. The NEC requires that the generator be capable of supplying the connected load without exceeding its rating. Adding an additional load that would cause the generator to exceed its rating would violate the NEC. Several factors must be considered when determining the generator's capacity. Firstly, the generator's kilowatt, often abbreviated as kilowatts, rating indicates its maximum power output. This rating must be sufficient to supply all connected loads. Secondly, the generator's voltage and current ratings must also be compatible with the connected equipment. Exceeding either of these ratings can damage the generator or the equipment. Thirdly, the generator's power factor must also be considered. The power factor is a measure of how efficiently the generator is using its capacity. A low power factor can reduce the generator's capacity. In this particular scenario, the generator's capacity is already a concern. Adding an additional load would only exacerbate the problem and increase the risk of overloading the generator. Before adding any additional load to the generator, it is essential to perform a thorough load calculation. This calculation should take into account all of the connected loads, including the existing load and the proposed additional load. The load calculation should also consider the diversity factor of the loads. The diversity factor is a measure of how likely it is that all of the loads will be operating at their maximum capacity simultaneously. If the load calculation indicates that the generator's capacity would be exceeded by adding the additional load, it is not permissible to do so. There are several alternatives to adding the additional load to the generator. One alternative is to upgrade the generator to a larger model with a higher capacity. Another alternative is to reduce the existing load in the generator by disconnecting some of the existing equipment. A third alternative is to install a separate generator to supply the additional load. Each of these alternatives has its own advantages and disadvantages. The best option will depend on the specific circumstances of the situation. In summary, adding an additional load to the generator in this scenario is not legally permissible because it would likely overload the generator and create a safety hazard. The NEC requires that generators be sized appropriately for the loads they serve, and adding an additional load that would cause the generator to exceed its rating would violate the NEC. It is recommended to perform a thorough load calculation and consider alternatives before adding any additional load to the generator. Additional explanation of the factors that contribute to the assessment. Firstly, NEC Article 220 provides guidelines for calculating branch circuit, feeder, and service loads. It outlines methods for determining the minimum size of conductors and overcurrent protection devices based on the connected loads. Secondly, NEC Article 445 specifically addresses generators, including their installation, wiring, and overcurrent protection. It emphasizes the importance of proper generator sizing and ensuring that the generator's capacity is sufficient for the intended load. Thirdly, the load calculation involves determining the total demand of the connected loads. This includes considering the nameplate ratings of motors, air conditioning equipment, and other electrical devices. The calculation also takes into account any applicable demand factors or diversity factors, which recognize that not all loads will operate at their maximum capacity simultaneously. Fourthly, the generator's capacity is determined by its kilowatt rating and voltage rating. The generator must be capable of supplying the calculated load without exceeding its rated capacity. Factors such as altitude and ambient temperature can also affect the generator's capacity. Fifthly, the automatic transfer switch is a critical component in the system. It automatically switches the load from the normal power source to the generator when a power outage occurs. The ATS must be properly sized and rated to handle the full load of the connected equipment. Sixthly, overcurrent protection devices, such as fuses and circuit breakers, are essential for protecting the electrical system from overloads and short circuits. These devices must be sized appropriately to protect the conductors and equipment they serve. Seventhly, continuous loads, such as motors and air conditioning equipment, are typically sized at 125% of their nameplate rating to account for the possibility of sustained operation at or near their maximum capacity. Eighthly, safety is paramount in any electrical installation. Overloading a generator can lead to overheating, equipment damage, and even fire. It is crucial to ensure that the generator is properly sized and that the electrical system is installed and maintained in accordance with all applicable codes and standards. Ninthly, when considering adding a new load to an existing generator, it is essential to perform a comprehensive load analysis. This analysis should take into account the existing load in the generator, the characteristics of the new load, and any potential impact on the generator's performance. Tenthly, if the load analysis indicates that the generator's capacity is insufficient to accommodate the new load, it is necessary to explore alternative solutions. These solutions may include upgrading the generator, reducing the existing load, or installing a separate generator for the new load. Let's delve deeper into the implications of overloading a generator. Overloading a generator poses significant risks to both the equipment and the safety of personnel. When a generator is overloaded, it is forced to produce more power than it is designed to handle. This can lead to several adverse consequences. Firstly, overloading a generator can cause it to overheat. The excessive current flowing through the generator's windings generates heat. If the heat is not dissipated quickly enough, the generator's insulation can break down, leading to short circuits and equipment failure. Secondly, overloading a generator can damage its internal components. The excessive stress on the generator's bearings, windings, and other parts can cause them to wear out prematurely. This can result in costly repairs or even the need to replace the entire generator. Thirdly, overloading a generator can reduce its lifespan. By constantly operating the generator beyond its rated capacity, its overall lifespan is significantly shortened. This can lead to increased maintenance costs and the need for more frequent replacements. Fourthly, overloading a generator can create a safety hazard. The overheating and potential for equipment failure can increase the risk of fire or electrical shock. It is essential to protect personnel from these hazards by ensuring that the generator is not overloaded and that all safety precautions are followed. Fifthly, overloading a generator can affect the quality of the power it produces. The voltage and frequency of the power may fluctuate, which can damage sensitive electronic equipment. It is crucial to ensure that the generator provides a stable and reliable power supply to all connected loads. Sixthly, the National Electrical Code NEC sets forth specific requirements for the installation and operation of generators. These requirements are designed to protect people and property from the hazards associated with generators. It is essential to comply with all applicable NEC requirements when installing and operating a generator. Seventhly, when selecting a generator, it is crucial to carefully consider the total load that will be connected to it. The generator should be sized to handle the maximum expected load, with a safety margin to allow for future expansion. It is also important to consider the type of loads that will be connected to the generator. Some loads, such as motors, require a higher starting current than the running current. The generator must be able to handle these starting currents without being overloaded. Eighthly, regular maintenance is essential for ensuring the safe and reliable operation of a generator. This includes checking the oil level, coolant level, and battery voltage. It also includes inspecting the generator's wiring, connections, and overcurrent protection devices. Ninthly, it is important to train personnel on the proper operation and maintenance of generators. This training should include instruction on how to start and stop the generator, how to monitor its performance, and how to troubleshoot common problems. Tenthly, always consult with a qualified electrician when installing or modifying a generator system. A qualified electrician can ensure that the system is installed in accordance with all applicable codes and standards and that it is safe and reliable. Going back to the original issue about the customer wanting to move an existing load to the generator, the short answer is that it is not advisable without a thorough assessment and potential modifications to the system. The primary concern is the generator's capacity. If the existing load plus the additional load exceeds the generator's rated capacity, it will create an overload situation, leading to the risks. It is important to emphasize the importance of adhering to the National Electrical Code NEC guidelines. The NEC provides specific requirements for sizing generators based on the connected load. Ignoring these guidelines can result in code violations and potential safety hazards. If the customer insists on moving the existing load to the generator, it is imperative to conduct a comprehensive load analysis. This analysis should involve measuring the actual current draw of the existing load under various operating conditions. It should also consider any future expansion plans or changes in load requirements. Based on the load analysis, it may be necessary to upgrade the generator to a larger capacity unit. This would ensure that the generator can handle the combined load without being overloaded. Another option is to implement load shedding strategies. Load shedding involves selectively disconnecting non-essential loads during periods of high demand. This can help to prevent the generator from being overloaded and ensure that critical loads continue to receive power. In addition to the generator's capacity, it is also important to consider the automatic transfer switch, often abbreviated ATS. The ATS is responsible for seamlessly switching the load from the normal power source to the generator during a power outage. The ATS must be properly sized to handle the full load of the connected equipment. It is also important to ensure that the ATS is compatible with the generator and the electrical system. The overcurrent protection devices, such as fuses and circuit breakers, play a crucial role in protecting the generator and the connected equipment from overloads and short circuits. These devices must be sized appropriately to trip or open the circuit before any damage occurs. Finally, it is essential to prioritize safety in all electrical work. Always de-energize circuits before working on them, use appropriate personal protective equipment, and follow all applicable codes and standards. By taking these precautions, you can minimize the risk of electrical shock, burns, and other injuries. Therefore, the answer is no, without assessment.